Hey there, it's Shannon Math Chick Myers. I hope you're having a wonderful day. We are now going to check out matrix operations. Matrices can be thought of as adjoined column vectors. They are represented in the following ways. You've seen this, capital letter, so usually A, B, or C till we get to some more specialized ones. You can also use something called the representative element. And this looks like capital A equals, and so you do the brackets like you use to enter in matrices into really any computing program, I think. And then you just say Aij. If it was matrix B, we would have said Bij. And then a rectangular array is another way. This was always the way that looked kind of scary to me when I was learning things about matrices, but it's really very informative, so try to take it that way. So you'd have maybe like a B11, B12, B13, all the way down to some B1n. This is for if B is of size m by n. And our next row would be what? Beautiful. First with B21, and then we'd have B22, B23, all the way down to B2n. And then it would continue down in this manner until you got to BM1. You're in the mth row, all right? This would continue down, and now you're in the mth row and second column. And then this behavior and this behavior goes on until you get to BMN, which is the entry in the mth row and nth column. Cool, cool? All right. So here we come to our first definition of the day. Definition of equality of matrices. So just like vectors, where the corresponding components had to be equal, we now are going to say that the corresponding entries are going to be equal in order, and it has to be true for every entry in order for two matrices to be equal. So, two matrices, A equal to Aij and B equal to Bij, are equal when they have the same size, which we'll call m by n to be general, and each of these entries, Aij, would be equal to Bij for 1 less than or equal to I less than or equal to m, because there's m rows, and 1 less than or equal to j less than or equal to n, because there are n columns. All right, so example 1, are matrices A and B equal? Please explain. So matrix A, what do you think? What size is matrix A? Good. We have 1 row and 4 columns. Cool. And then B is size. Good. 4 rows by 1 column. Are these the same size? No. A and B are not the same size. Okay. Now let's take a look at example 2. We want to find x and y. We will use matrix equality to solve for the unknown values. Groovy? All right, so here we go. First, check the size. So do you see that the matrix on the left side has dimension 2 by 2, as does the matrix on the right side? Now, One interesting thing about the entries for matrices is that, you know, unless otherwise stated, the entry in the first row, first column is not going to be dependent on any of the other entries in that matrix. So what that means is that we don't get a system of equations to solve for these two unknowns. We get two separate linear equations in one variable to solve. Groovy? All right, so let's go ahead, and what would we equate 2x minus 1 to? Beautiful. -5, because 2x minus 1 and -5 are in the first row, first column of each matrix. Make that a little nicer for you. And now, let's just go ahead and solve it. When I isolate the x, I'll have 2x equals -4, and x will equal to -2. So that one is done. And next up, we will have the equation for the entry in the second row, second column. So this entry, y cubed, must be equal to, awesome, 1/8, because 1/8 is in the second row, second column of the matrix on the right-hand side. Okay, so let's do this. Let's just separate them a bit, and we'll have y cubed equals 1/8. Do you remember your algebra? How do we solve this? Cool. You can either raise both sides to the 1/3 power, or you can find the cube root of both sides. Now be careful when your root has an odd index, which we do because our index is 3, you can get negative values underneath the radical because it's a cube root. You're multiplying something to itself an odd number of times. So let's see what happens. This will give us y, and y will equal to, well, 1/2 cubed is 1/8, so we'll just get 1/2. And then that's our answer. Good? Alrighty, so moving along, we have a matrix that has only one column is called a column matrix. Wow, something in math is named very aptly. I love it when that happens. Or column vector, depending on how you want to think about it. A matrix that has only one row is called, what do you think? Awesome, a row vector. Actually, I'll say row column first, or row vector. As we learned earlier, boldface lowercase letters often designate column matrices. And row matrices. Okay, so let's just take a look at the next idea that we'll be using, notation that you see a lot. Suppose we have a column matrix that's equal to A1, and let's say that that is A11, A21 when we write it as a rectangular array. And suppose we also have this column matrix A2, and that would be A, beautiful, 1, 2, A2, 2. And suppose we wanted to adjoin these matrices. So you'd have something that looked like this. Some capital A is equal to the matrix, column matrix A1 and the column matrix A2. Isn't that cool? And then your matrix A could also be written using the entries of the matrix. Cool, cool? So just so you can see what, corresponded to each other, you'd have, this was our matrix A1, and here it is here and here in the big matrix A. And then we had column matrix A2, which was in the second column, surprise, surprise, of A. And then written out in the rectangular array, this is what we have. All right, next up, definition of matrix addition. So if A equals Aij and B equals Bij are matrices of size m by n. They have to be the same size. Then their sum is the m by n matrix given by A plus B is equal to Aij plus Bij. Cool, cool? All right, the sum of two matrices of different sizes is undefined. On to definition of scalar multiplication. If A is equal to Aij and it is an m by n matrix and C is a scalar, then the scalar multiple of A by C is the m by n matrix given by C times A is equal to C times Aij. Groovy? Okay, so we've got those two definitions down. So let's practice. Now let's also note that you can use negative A to represent the scalar product -1 times A. If A and B are of the same size, then A minus B represents the sum of A and, you got it, -B. So for example 3, find the following for the matrices. We're looking for the sum and then some, fun stuff, scalar multiple and difference. All right? So if you feel comfortable, go ahead and pause the movie and then start playing it again to see how you did. All right? So A plus B is equal to, by definition, what do? Beautiful. We add the corresponding entries. So we'd have 1 plus 5 for the first row, first column entry. We would have -3 plus 2, 6 plus 7, and that takes care of the first row. And then we'd have 2 plus -1, and then 0 plus 9, and 2 plus -4. And lastly, we would have -2 plus -3, 8 plus 0, and then -1 plus 1. So hopefully you can see where all those came from without me highlighting everything. I think that'll get a little busy. All right, so this in turn will equal to what? Beautiful. 6, -1, 13, 1, 9, -2, and -5, 8, and 0. And that's our result. All right. So next up, we've got our 2 times A minus B. So 2 times A minus B equals 2. Well, by definition, what is 2 times A? You can bring that constant in. So I'll do more work on this one. You'd have 2 times 1, 2 times negative 3, 2 times 6, 2 times 2, 2 times 0, 2 times 2 again, and then 2 times negative 2, 2 times 8, and 2 times negative 1. And then what are we doing with that? We're adding negative b. So actually, let me rewrite that. So we'll have 2 times a plus negative b. So now, let's see what we're doing. Negative b means I'll just flip the signs on each one. But again, I'll show you the work this time around. Most of it we would usually do in our head. Cool, cool? All right, so then what's going to happen? We're going to end up simplifying, what do we have? Well, I'll have 2 plus negative 5 is negative 3. And then negative 6 minus 2 is negative 8. I'm going on the first row first. And then 2 times 6 is 12. Plus negative 7 is positive 5. And then 4 plus negative 1 times negative 1 would be 5. 0 minus 9 is negative 9. 4 plus 4 is 8. And then negative 4 plus 3 is negative 1. 16 plus 0 is 16. And negative 2 plus negative 1 is negative 3. All right, so on to matrix multiplication. Matrix multiplication is a wee bit more challenging, right? So just hold on, you can do it. We will get through this, but you really have to pay attention to what's going on. And yes, you do have to know how to do this by hand because I believe it's important for you to understand later concepts. So I will test you on doing this by hand when you don't have the use of a calculator. So here we go. If A is equal to Aij and it is an M by N matrix, and B equal to Bij is an N by P matrix, then the product AB is an M by P matrix. So if you were to name the product A times B equal to some matrix C, and this would in turn be equal to, in the representative element form, Cij. Multiplying Aik times Bkj means that we are multiplying the entry of A that is in the ith row and the kth column to the entry in B that is in the kth row and the jth column. That is why the number of columns in A has to match the number of rows in B. Groovy? Okay, so if we expand this out just to give you an idea, we would end up having A, I, 1, B, 1J, plus AI2, B2J, plus, and you keep going in that manner until you get down to AIN times BNJ. Groovy? All right. So In plain words, to find an entry in the ith row and the jth column of the product A times B, multiply the entries in the ith row of A by the corresponding entries in the jth column of B, and then sum the results. So let's check it out. All right. What I do usually is A is what? What size? A is size 3 by 2, right? 3 rows, 2 columns. And what size is B? Beautiful. 2 rows by 4 columns. So as long as the insides match, all right, meaning if you put them side by side, that would make the columns in A be equal to the rows in B. That tells you it's okay to do the multiplication. Now, over here, the 3 here and the 4 here is going to give us the dimension of the matrix, which is the product. So I always match these things up. I always write them side by side just to make sure I'm not making up my own math, all right? So don't feel bad if you need to do that. I don't. So here we go. Let's take a look at how we would do this, all right? I'm trying not to get this to be too colorful. But if we do our A times B, this is what we will get. And I'm just going to go straight to A times B. I'm not going to worry about renaming it C. That just takes a little more time. I do know I'm going to have 3 rows and how many columns? Beautiful. 4 columns. And we want to give ourselves a lot of room because I'm going to write everything out about how to do this. So here we go. We are going to take the entries in the first row of A and the first column of B, and we are going to add those scalar multiples, all right? So let's do it. So for our very first entry, we're going to be using 15 in A times negative 12 in B. Good so far? And then plus the 0 in A times the awesome negative 13 in B. I'll go nice and slow for this one so that you can see what matches up. So our next multiplication will be what? Awesome. I still use that first row for A, but now I got to use the second column in B. So I'll have my 15 times 7 this time, plus 0 times, good, 1. And so we have this time, I'll do this in the green. And next up, what's going to happen? Awesome. We're going to still be using that first row, so 15 times, and we'll be now on the third column in B. So 15 times 5 plus 0 times, awesome, 2. And lastly, and the last one for the entries that are in the first row of that resulting matrix are going to be what? Beautiful. We'll have 15 times -1 plus 0 times 11. Cool, cool? All right, so this row, I'll do in more of a red. All right, so now we're on to the second row of A. So for our second row of A, let's do, I don't know, purple? Light purple? No, that'll be too much like the other one. Light blue. All right, so we'll have 4 times -12, so we're back to the first column of B, and then plus 5 times -13. So that'll give us, in this one, we have our 4 and our 5 now. And then we used what? This purpley color for this column here. And now we have 4 times 7 plus 5 times 1. Then we'll have 4 times 5 plus 5 times 2. And we'll have 4 times -1 plus 5 times 11. So these are what we used from matrix A in the second row. And then our columns are this one here. Okay, and lastly, we've got the third row in A, and then we'll use all the different columns in B. So, -3 times -12 plus 1 times -13, -3 times 7 plus 1 times 1, -3 times 5, 1 times 2, -3 times -1 plus 1 times 11. And we'll just use this pink color. All right, and now simplifying all of the operations inside the matrix, what will we have? So the first entry is going to give us what? Beautiful, -180. And then the first row, second column will be 105. First row, third column will be 75. First row, fourth column will be -15. And then second row, first column, -113. Second row, second column will be 33. Second row, third column will be 30. And second row, fourth column will be 51. And lastly, the third row, first column will have 23. Third row, second column, -20. Third row, third column, -13. And third row, fourth column, 14. Cool, cool? And that is our... All right, so hopefully everything went okay. And now let's just do some practice stuff here. Go ahead, pause the movie, see how you do. I'm going to work quietly here, and so that way you can, just do your thing, and I'll fast forward the video. Cool, cool? All right. About the next couple questions. Is matrix addition commutative? Well, let's see. We looked at A plus B, and we got this result here. We looked at B plus A and got this result here, which is the same. So we haven't proved anything, okay? But I would give this a, it looks like it may be. What about matrix multiplication? Well, when we did our A times B, we got that first result. B times A gave us this result, which is not the same. So we can say definitely for sure, heck no. All right? It's not commutative, because if even one of them doesn't work, if even one case doesn't work, then you can't say it in general for the whole group. Okay? Okay, let's take a look at this equation down here. We've got a matrix product, right? So let's play around with this. Okay, what if this was like column A1? Remember, like we did before, column A2? So these would be column matrices. And this would be column A3. Often what you'll see is the variable column, it'll often be called X or Y. So this is our X column. And then the column of constants we talked about before would be B. All right. Now, A1, A2, and A3, when you adjoin them, the coefficient matrix A is equal to, in this case, these column matrices, A1, A2, and A3, which are adjoined. Groovy? Okay, well, let's check this out. So it turns out by performing the matrix multiplication, A times X, right, and equating it to the matrix B, this system results. So you'd end up with A11X1 plus A12X2 plus A13X3 is equal to B1. And then A21X1 plus A22X2 plus A23X3 is equal to B2. And A31X1 plus A32X2 plus A33X3 equals B3. Groovy? All right, so now let's take a look at example 6. We want to write the system of equations in the form A times X equals B, where X and B are column vectors, and solve this matrix equation for X. Groovy? All right, let's do it. So just to give you a heads up, we are going to learn a bunch of different ways to solve systems of equations. Many times, multiple methods will work out, okay? You're going to learn all of them so that you know best what tool to use for what situation. Groovy? All right. So here we want to look at, okay, well, why don't we just look at it? What is our matrix of coefficients? Beautiful. 2, 3, 1, and 4. How about our matrix of variables? Awesome. Let's just call it X, and that's equal to X1, X2. And then, very good, we'd have our matrix of constants, which will be B1 and B2. So now let's go about finding the directions and solving the system. So the way to represent it would be A times X equal to B. And so that would be A, which is 2, 3, 1, 4, times X, which is X1 and X2. And that is equal to, our matrix of constants was what? We had a 5 and a 10. Okay, so here we go. If we take a look at this one, since we don't have any background yet with inverses of matrices, what we're going to do is we're going to use the augmented matrix that consists of the matrix A of coefficients and our matrix B of constants, and we're going to have this situation here. Good so far? And we learned how to do this stuff last time, did we not? So what we're going to do is we need to zero out the 1 that is in row 2, column 1. So to do that, let's go ahead and say negative row 1 plus 2 row 2. And that's going to give us a new row 2. Cool, cool? So let's check it out. Our row 1 stays the same, so I'm just going to rewrite it as it was. And our new row 2 is going to be awesome, 0, just like our evil plan. And then negative 3 plus 8 will be positive 5. And then we'll have negative 5 plus, let's see, 2 times 10 is 20. So that'll give us 15. Cool, cool? All right, so next up, what should we do? Let's go ahead and do this. Do you see that we can take 1/5 times row 2 for a new row 2? And that will give us the matrix 2, 3, 5. And then we'll have our new row 2 as 0, 1, and 3. And now what we want to do is we want to zero out the 3 that is in row 1, column 2. To do so, what's going to have to happen? Beautiful. If we do negative 3 times row 2 plus row 1 for a new row 1, what will we get? Well, row 2 will stay the same this time, and the change will be in row 1. So, let's see. We'll still have a 2 in the top left. First row, first column has 2 in there. And then our evil plan was to get a 0 here, and that works, right? Because we'll have negative 3 plus 3 is 0. And then we'll have negative 9 plus 5 is negative 4. Cool, cool? All right, well, let's go ahead and do one final step here. If we just take 1/2 times row 1 for a new row 1, then we'll have row 1 looking pretty. So we'll have the matrix, let's see, 0, 1, and 3. And our new row 1 will be 1, 0, and negative 2. So just a little bit of a reminder, these ones right here are called leading ones or pivots because we have this in reduced row echelon form. And so basically what that means is that your coefficient matrix is going to be a diagonal matrix with 1s as all of the diagonal entries. Cool, cool? All right, so now let's take this back into a system so I can show you what we found, all right? So A times X equal to B is this following system. We will have A, which was what, 2, 3, 1, 4, times the matrix of variables. Well, what did we find here? We found that X1 was negative 2, and x2 was 3, did we not? So we'd have negative 2, 3 in that column matrix. And that should equal, if we did everything right, that should equal to 5, 10, that column matrix. Cool, cool? So our X matrix is equal to, and by the way, you didn't have to write this step. I just wanted to show you what we found. All right? Our X matrix, which is at the end of the day what we wanted to find, is equal to the column matrix negative 2, 3. Groovy? All right. Okay, so let's do some more on partition matrices. So I've kind of gone into depth on these. What we want to look at are linear combinations. We deal a lot with linear combinations. So the matrix product A times X is a linear combination of the column vectors A1, A2, A3 down to column vector AN that form the coefficient matrix A. So A times X, it turns out, can be written as X1 times A11, A21 down to A M1 plus X2 times A12, A22, all the way down to A M2. And we go on in this manner until we got to Xn times, someone's really having fun out there, times A1n, A2n, all the way down to AMN. Cool, cool? All right. So what we've shown is that this product is a linear combination of these column vectors in the coefficient matrix. And it's amazing because we can learn a lot about spanning with that. All right. And then we'll be able to apply all those ideas to matrices. Cool, huh? So here, just so you can keep track, this one here was like our A1, A2, and then this was like our AN, right? And so, well, A times X then would be, I'll write it here, A times X could be written as X1 times column matrix A1 plus X2 column matrix A2 all the way down to Xn times column matrix AN. Now remember, those Xi's are constants, right? Or belong to the real numbers. They're not necessarily constants, but we would find those instead of the coefficients this time. Groovy? All right, well, does it make sense then that the system A times X equal to B is consistent if and only if B can be expressed as such a linear combination where the coefficients of the linear combination are a solution of the system. Notice it says a solution. There might be more than one. Okay? All right, so now example 7, let's take a look at this guy. We want to write the column matrix B as a linear combination of the columns of A, if possible. So we have our A, we have our B. Let's go ahead and write our X matrix. So how many variables would we have? Beautiful. We would have X1 and X2, or X and Y if you want to do it like that. So here we go. Just like before, right? Remember how we were saying, oh, okay, some matrix U, can it equal to a constant times V1 plus another constant times V2? Well, what we want to do is find out if B can be written as a linear combination in this way, where we would have x1 times a1, so this could be a1, and we could have this be a2, plus x2 times a2. Groovy? All right. Well, we know some of this stuff, right? We know that B is equal to what? Good. -7 and then 63. And then we don't know x1 and x2, so they'll be what we're finding this time to complete our linear combination. But we do know a1 and a2. So a1 is -116 and a2 is 3, 1. So we'll have our x2 times 3, 1 as a column matrix. All right? Okay, well, just like before, I mean, we kind of go through and we do this stuff. I'm going to work it on the side so that we can come back and plug it in nicely. So here we go. We are going to have what? To complete that linear combination, we need to multiply and then add corresponding components, right? So we're going to have x1 times -1 plus x2 times 3 for our first entry in the first row. We'll have only one entry in each row. And then we're going to have, for the second row entry, we'll have what? x1 times 16 plus x2 times 1. And we want that to equal to our B matrix, which is -7 and then 63. Cool, cool? All right, well, we've got one happy column matrix, so this will end up being -x1 plus 3x2, and then we'll have 16x1 plus x2, and that's got to equal to -763. So by matrix equality, can't we equate these components? So we would have -x1 plus 3x2 equals -7, and then 16x1 plus x2 is equal to 63. Cool so far? Okay, so here we go. On this one, let's just go ahead and... Okay, so this corresponds to the augmented matrix. -1, 3, -7, and then 16, 1, 63. So to get rid of the 16 that is in the second row, first column, we want to zero that out. So we'll need to do 16 row 1 plus row 2 for a new row 2. And that'll give us what? Beautiful. We'll have our first row the same, and then we'll have what? For our second row, this will zero out as planned, and then we'll have 48 plus 1 is 49, and then we'll get, let's see, when we multiply 16 times -7, we'll get -112. And then that's going to give us what? -112 plus 63 is -49. And so this corresponds to the system negative x1 plus 3x2 equals negative 7, and 49x2 equals negative 49. So do you see that x2, when we isolate that, will be negative 1, and then plugging in negative 1 for x2 in this top equation, we'll have negative x1. Let's see, we'd get minus 3, then we add that to the other side, we'll get minus 4. So then x1 would be positive 4. Cool, cool? All right. And then just to show you, I plugged in negative 1 in for x2 there to solve for x1. So let's check it out. We're going to have here, we can put this back. So it turns out that the column matrix negative 7, 63 can be written as x1, which was what, 4, times negative 1, 16, plus x2, which we found to be negative 1, times 3, 1. And if you do the math on the right side, you'll see you get the same thing as the B matrix. Isn't that groovy? All right. So here, let's see, this was my x2 that we found, and our x1 was what? Our x1 is 4, so that's what we plugged in here. Cool, cool? And we are on to example 8. Ready? Okay, let's find the products A times B and B times A for these diagonal matrices. So go ahead and pause the movie if you'd like, and then we'll see how you do. Okay, let's see how you did. A times B is equal to what? We would have 3 times negative 7, right? Plus 0 times 0, and then plus 0 times 0. And then for the second entry, what's going to happen? We'll have, so first row, second column, we'll have 3 times 0 plus 0 times 4 plus 0 times 0. And then first row, third column entry will be 3 times 0 plus 0 times 0 plus 0 times, plus 0 times 12. Cool, cool? All right, and then now we'll use the second row of values. So we'll have an A and then we're on the first column. So 0 times negative 7 plus negative 5 times 0 plus 0 times 0. And then for our second row, second column entry, what's going to happen? We'll have 0 times 0 plus negative 5 times 4 plus 0 times 0. And then for our second row, third column entry, what are we going to have? 0 times 0 plus negative 5 times 0 plus 0 times 12. All right, on to the third row. What's that going to be? Well, that's going to end up being 0 times negative 7 plus 0 times 0 plus 5 times 0. And then we'll have 0 times 0 plus 0 times 4 plus 5 times 0, and then 0 times 0 plus 0 times 0 plus 5 times 12. Well, this is equal to negative 21, 0, 0, 0, negative 20, 0, and then 0, 0, 60. Pretty cool, huh? Well, why don't we see what b times a is? How would it be different? Be careful going the other way. We would have negative 7 times 3 plus 0 times 0 plus 0 times 0. Our next entry would be negative 7 times 0 plus 0 times negative 5 plus 0 times 0. And then our next entry in our last entry in the first row is going to be negative 7 times 0 plus 0 times 0 plus what? Good, 0 times 5. Cool, cool? All right, and then our second row. Okay, look at that. What are we going to get? Cool. It's weird, right? We're going to get negative 21, 0, 0, 0, negative 20, 0, and then 0, 0, 60. So what do we notice here? Awesome. It's looking like what? Maybe multiplication of diagonal matrices of the same order, size, right, is commutative. Cool, cool? All right, so now here's another technique where you can multiply matrices. It's just a different way of organizing your work, honestly. So, and you don't have to use this if you don't want to. I just kind of wanted to do it for you so you could check it out. Basically, you can partition some both matrices, just to make the multiplications seem a little less crazy. So if we call A, and we say that that's equal to a series of matrices that we adjoin, right? So let's just call this matrix capital A11, capital A12, capital A21, and capital A22, right? And then we could say that matrix B is equal to capital B11, capital B21. Cool, cool? All right. Well, if you were to take a look at this, right, how would we find AB in terms of, these big matrices? So let's check it out. So A times B is equal to, well, we'd have A11 times B11 plus, beautiful, A12 times B21, and that would be what? What's the size of the matrix we're going to get? You know, I mean, matrix A in this form is what? 2 by 2. And matrix B is 2 by 1. So do you see we're going to get a 2 by 1 out? So that completes row 1. And then row 2, let's see what we get. We'll use the second row of A, and we'll have A21 times B11 plus A22 times B21. Cool, cool? Well, so what does that mean? Well, if we partition these, then what we could say is that I could find these different products, right? And then break down my work. So let's do it. A11 is equal to 2, -1, the way it's been partitioned is a column matrix. A12 is equal to the column matrix 1, 0. A21 is equal to the 1 by 1 matrix 3. And A22 is equal to the 1 by 1 column matrix 1. And B11 equals the row matrix 3, 0. 2, 1 will be what? 2, 1. That's kind of funny. All right, so A11, remember, is 2, 1 times B11 will be the row matrix 3, 0. So when I do that multiplication, I've got a 2 by 1 times a 1 by 2. So I'm going to get a 2 by 2 out. So I'll have 2 times 3 is 6. 2 times 0 is 0. 1 times 3 is 3. 1 times 0 is 0. Groovy? Now for the next one, I need to do A12 times B21. So A12 is 1, 0. And then B21 is 2, 1. That's going to be also a 2 by 2 matrix. So we'll have 1 times 2 is 2. 1 times 1 is 1. And then 0 times 2 is 0. And 0 times 1 is 0. Groovy? So my first entry in here is going to be, when I add these two together, what is going to happen? I'll have 6 plus 2 is 8. And then I'll have what? 0 plus 1 is 1. And then second row, 3 plus 0 is 3. And then what's the last one? It'll be 0. And I'll keep these partitioned for the moment. And then what's going to happen? So this, by the way, corresponds to this matrix here. All right, so then for our next stuff, what do we have going on? We have by the way, this is we added these. All right, and so for the next one, what do we have? We have, do that in purple. So we'd have A21 times B11. So A21 was 3. B11 is 3, 0 as a row vector. And that's equal to what? We have a 1 by 1 and a 1 by 2, so we'll get a 1 by 2 out. Okay, so that means we'll get a 1 by 2 out, so 1 row, 2 columns. So then we'll have what? Beautiful. 3 times 3 is 9, and then 3 times 0 is 0. It's really a scalar times that if you look at it. And then our next one was going to be A22 times B21. So A22 was just 1, and B21 was 2, 1. And then that, again, will be 1 by 2. So when we do that computation, we'll just get 2, 1. So what we're doing with these guys is we are adding them. So when we add them, what are we going to get? We'll get the matrix, beautiful, 11, 1. Well, we don't need to keep it partitioned, so why don't we write this as one happy matrix, and this will be 8, 1, 3, 0, 11, 1. Okay, so that's one way of organizing your work when you're doing matrix multiplication, or for coding maybe. It just depends on what it's useful for. And that corresponding one was, this guy was the red one, and then the sum of those two. So then we get our result in the end. Cool, cool. That's it for today. I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, hey, please subscribe. Bye.